Hello everyone and welcome to Lecture 3 Part 3 in which we investigate the Visionaire Cipher. Before we do so, let us summarize what we've seen in Part 1 and 2 to see why this new scheme is necessary. Indeed, the Caesar cipher offers only 26 ways to encrypt a message, while the affine cipher does not offer much better, only 312 different keys. Therefore, both of these ciphers are not secure against brute force attack. We've also seen that these two are special cases of the Substitution cipher, which offers 26 factorials, the number that you can see on the screen, different possible keys. This number is quite big, and I hope that you agree that 312 offered by the affine cipher is nothing in comparison with it. Now, what if we imagine another substitution scheme which gives more possibilities than the affine one? Would it be secure? Well, as you probably expected, the answer to this is a no. And actually, all substitution ciphers are easy to code break using frequency analysis, as we shall see in the following example. Imagine Eve intercepted the message you can see on the screen. To this ciphertext, we apply frequency analysis by first counting the letters to get the table that you can see here, in which A occurs 13 times, B occurs 63 times, etc. Of course, to count these letters, I wrote a little computer program in Python for our purposes. Now if you get back to our ciphertext, we see that the two most common letters here are W and H. And the table that you can see to the right represents the frequency of letters in the English language. And we see that the two most common letters are E and T. Therefore, we might guess that in our ciphertext, E is encrypted as a W and T is encrypted as an H. And this is what we get when we replace W by E and H by T. Now, if we take a closer look to this modified ciphertext, we see that the pattern TKE appears many times here, like here and here. And we know from the English language that TKE should correspond to the. We deduce from this that the letter H was encrypted as a K, and we get this text once we do the substitution. Let us now get back to our frequency analysis table, from which we see that C, D, and V are the most secure letters after W and H. Now, from our famous table of frequencies of the English language, we know that the most secure letters after E and T are A, O, and N. Thus, C, D, and V are probably A, O, or N. This isn't very helpful, but notice, however, that the pattern DD occurs many times in our text, and in English, among A, O, and N, only O appears in this fashion. Therefore, we replace all the D's by O's to get what you see on the screen. Now that we know that D is an O, we're left with two remaining choices for C, either it is an A or it is an N. But there is something that everybody should know. The bigram AN is very common in English texts. And we see that the pattern CV occurs very often in our ciphertext, from which we deduce that AN here is actually equal to CV. Thus we see that C encrypts an A, and V encrypts an N, and this is what we get once we do the substitutions. Now it is a matter of time to code break this substitution cipher. If you take a close look to our text, you notice here that we read on the one hanks. On the one hanks, of course, in English is on the one hand, so X corresponds to a D. Now that all the X's are replaced by D's, we clearly read here on the other hand, which means that the Y here corresponds to an R. We once again do the replacements, and we see here that this word might be the word today, and we would hope that the P here is a Y. Now we see that the word here, DL errand, occurs many times in the text, and we assume that this is the word different, which means that L corresponds to an I and the letter Z corresponds to an F. And now we read here for 10 year B, which might be actually for many years, so T corresponds to an M and B corresponds to an S. Now the word here is American, and actually this is American, so G is a C. Reading the ciphertext again closely, one sees that this word actually is dilemma, so U corresponds to an L. In the same fashion here we read the A rate American, which probably gives the Great American, and the letter A corresponds to a G. Now for the text to make sense, the letter here should be a V and the letter O should be a W. So we get here, for many years I have wanted to write the Great American, differential, etc. Now if you have the eagle's eye, you would notice that this word here, genetrating, is actually the word penetrating, so J is a P. This is what we get after substitution, and notice that the word Rus here is actually the word book, so R is a B and S is a K. Substituting again, we notice here that this word might be the word is actually the word education. We deduce from this that the letter M is U, and then actually doing the same thing, the letter I is the letter J, and the letter F is the letter X. Our plain text is from Michael Spivak, great book, A Comprehensive Introduction to Differential Geometry, and I hear myself in these lines. Of course, I did not encrypt this letter by letter, and I wrote a little computer program in Python that you can see on the screen. Now that we're done, many lessons are to learn from this attack. First of all, although we have a huge number of possible substitution, this does not make the substitution cipher secure at all. And this highlights how powerful frequency analysis is. Second, what made substitution ciphers vulnerable to frequency analysis is the fact that we always encrypt each letter the same way, and in our example, the letter E is always encoded as a W, and this security flaw makes it breakable by counting letters. So in order to build more secure ciphers, one has to think of a scheme in which a given letter is encrypted differently depending on its position in the plain text. Here enters the famous Visionaire Cipher, first invented by the Italian cryptographer Giovanni Battista Balazzo in 1553, and rediscovered by the French cryptographer Blaise Vigenere in 1586. Let us see how it works on a concrete example. In what follows, we will try to encrypt the profound statement numbers measure size, groups measure symmetry, which I took from Armstrong's great book, Groups and Symmetry. First of all, we split our plain text into blocks of 5 letters to avoid word length attacks and get what you see on the screen. Now, in order to encrypt our plain text, we choose a keyword which is going to be math for us and write it repeatedly underneath the plain text. Once this is done, we add the plain text to the key stream to get our ciphertext. For instance, n plus m corresponds to 12 plus 13, which is 25, and we know that 25 corresponds to the letter Z. Moreover, we know that A corresponds to 0, so U remains unchanged by our encryption. To do this systematically, I of course wrote a little computer program in which there is a first function convert key, which will convert the key math to a list of numbers. Thus, when we type convert key in the shell for maths, this is what we get as a list in which the numbers 12, 0, 19, and 7 correspond to the position of the letters M, A, T, and H in the alphabet. And now we type in our shell Visionaire of our plain text, which is numbers measure size, groups measure symmetry, with our key math, and we get the following ciphertext. Let us now take a close look and compare the plain text and the ciphertext. We see, for instance, that the letter M here is encrypted as an F, and then it is encrypted as a T, and here it is encrypted as a Y. This obviously shows that the Visionaire Cipher encrypts letters differently according to their position in the text. We now investigate this new scheme to see how it improves the security of substitution ciphers. To do this, we get back to our text about differential geometry, and the graph that you can see on the screen is the frequency of letters in this text. When we encrypt our plain text with a substitution cipher, this is what we get, and this is the frequency of letters to the right of the substitution cipher text. What we obviously see here that frequencies in the plain text and frequencies in the substitution text are the same, but for different letters. However, if one applies the Vigenere encryption to our plain text, one gets the following encryption and this graph to the left, which is the Vigenere distribution of letters. Interesting. In comparison with the substitution cipher, we see that here the distribution of letters is almost the same for every letter and is smoother, which makes it very hard for an attacker to use frequency analysis and code break the Vigenere cipher. For this reason, this letter was known as the unbreakable cipher for 100 years, and it is indeed harder to break than any substitution cipher, but we will see that it has its own flaws too. For our purposes, we suppose that the attacker knows the length of the key, and in our case, the key is math and its length is 4. Thus, we start putting our ciphertext into blocks of 4 letters, 4 here, and so on and so forth. And we notice that we can divide our text into 4 groups of letters in the following fashion. The first group contains the first letters of each block of 4. So, for instance, in our first group, we will find the letter R here, and then the letter M, and then the letter Q, U, etc. The second group of letters will contain the second letters of each block, in which case its elements will be the letter O here, the letter N, the letter A, the letter H, and so on and so forth. We define the remaining groups in the same manner, and here what we get, as you can see on the screen. To do so, I of course use this little computer program in which number is the number of the group that we're looking for. Now what is common between letters in group 1 is that they are all encrypted by adding the letter M to the plain text. In group 2 they are all encrypted by adding the letter A to the plain text, in group 3 by adding the letter T, and in group 4 by adding the letter H. Thus, every group of letters can be considered as a Caesar cipher, and one can use here frequency analysis to code break it. So in each case here, it is all about finding of how much we shift our alphabet to get group 1, and how much we shift our alphabet to get group 2, and so on and so forth. So after applying frequency analysis to each group, this is what we get as distribution of letters. We see here that the most common letter is Q, which occurs 36 times, and we know from English that the most common letter is E, so we must have added 12 to the letter E to get the letter Q, and we know from the alphabet that 12 corresponds to the position of the letter M. This means that the first letter of the key of the Vigenere cipher is M, which is actually true. Now if we take a look into the second group, we see that the most common letter is E itself, which means that actually E was encrypted as an E, and this happens when we shift by 0, in which case the second letter of the key is the letter A, which is also true actually. I claim that we're almost there because we are recovering step by step our key math, which makes the Visionaire cipher breakable. And let me remind you that recovering the key math makes the ciphertext very easy to decrypt. To make sure that this works, we actually see that in group 3 the most common letter is X, and the difference between X and E is 19, and we know from the alphabet that 19 corresponds to the position of the letter T, which makes it M, A, and T, and this surely corresponds to the word math. Now this was an easy job to code break the Visionaire cipher, but let me remind you that we made a great assumption about the attacker, that he knew that the length of our key was 4. Now the good question is this information easy to get? This is actually not very difficult to do, and the interested student can check Friedrich-Kasiski test to see how things are done. Our lecture ends here, and we will investigate more ciphers in future lectures. Thank you for listening.